Good evening, everyone, and welcome to CERN. I'm Davide De Biasio from the CERN Courier editorial team, and tonight I'll be your host from the CERN Control Centre, where our experts are operating the world's largest and most powerful particle accelerator, the Large Hadron Collider. Its 27-kilometer ring is buried 100 meters under the border between France and Switzerland. Inside, protons and heavy ions accelerate to near the speed of light and smash together to discover new particles, study the ones we know, and understand how matter behaved right after the Big Bang. In just a few days, this remarkable machine will deliver its final collision, and it will then turn silent for a while. Over the next 4 years, it will transform into the High-Luminosity LHC. To guide us through this journey, we are joined tonight by Bettina Mikulec, Oliver Brunig, and Gauthier Hamel de Montchenot. We're also connected via Zoom to the 4 experiment islands, Atlas, Alice, CMS, and LHCb. But before moving on, let's go over to Emma at the LHC island.
Thank you, Davide. I'm Emma, I'm part of the CERN communications team, and I'm here with Jörg Wenninger, an accelerator physicist in the operations group. So Jörg, can you tell me what's happening right now on the LHC island?
At the moment, we're providing ion beams for the LHC experiments. In fact, the beams have just been accelerated, and we're just preparing the collision. So in about 2 minutes, the beams will start colliding, and the experiments will start to take data for another LHC fill.
Exciting. So I know often the LHC collides protons, so how often do you do these heavy ion runs?
Now, the number of days that we spend on heavy ion depends a bit on the requests of the experiment and their interest for proton versus ion data. Typically, we run about 10% of the year, so about a month with ions every year. Yes.
And what different types of particles have you accelerated over the LHC's years of operation?
Of course, so far we had the workhorse was protons. Our second workhorse in ion was lead beams. But we also accelerated occasionally xenon beams, oxygen beams, and neon beams.
So can you tell me what exactly you're doing right now just to prepare for these collisions?
So at the moment, the operator, which is just sitting here behind us, is actually running the sequences. The beams at the moment are still not colliding, so they're separated at the collision point. And in fact, we're slowly ramping down the magnets now to actually produce the luminosity.
Great. And can you tell me what will happen next, so after this run even?
So this run will last until coming Sunday. At 7 a.m. we stop the ion run. It will be the last actually physics of the LHC in run 3. Then we have about 2 weeks where we test the beams in view of the HL-LHC. And in fact, on the Saturday 26 at 6 a.m., in fact, the last beam will leave the LHC for the next 4 years before HL-LHC comes on.
Thank you very much. Now we're going to go back to Davide.
Many thanks, Emma. Before we turn to our wonderful guests, let's watch a short film that takes us on a journey through the history of the LHC and its experimental program.
I think it's generally accepted that the kickoff of the LHC project was the Lausanne workshop in March 1984.
The Large Hadron Collider project will ensure Europe's leading role in particle physics research well into the 21st century, while making maximum use of the CERN existing facilities. It's now up to CERN Council to decide if and how the project should be encouraged and to set the appropriate condition in view of its eventual approval. Thank you.
Once we have this 27-kilometer long tunnel in which we are going to make an E plus E minus collider, which will be the lab, at one day, possibly, we could put in a proton-proton collider, which would allow to go to much higher energies.
The last 10 years have been quite active. And you see, people have been so motivated that they were working like mad. And now we are ready to see the benefits. And I think they will achieve something they can be proud of.
These kind of detectors and experiments come about once in a generation.
The adventure of the LHC construction is finished. Now let the adventure of discovery begin. Thank you. Yes, sir. Yes.
And here's the beginning of the process, the first proton beam being injected.
After 10 days, while ramping up the current in the accelerator's magnets in preparation for 5 TeV running, an unexpected failure happened in one of the LHC's 8 sectors.
It went wrong what we call the connection here to this superconducting cable.
An awful lot of analysis went into understanding what happened and trying to make sure it never happens again.
But this time the beam was in such good shape and making so many turns.
It's a very, very encouraging sign and remarkable progress.
If you want to produce something very massive, you need a lot of energy.
We have a discovery.
This boson is a very profound thing that we found. Okay, this is not like other ordinary particles. It really is we're reaching into the fabric of the universe at a level we've never done before.
So we'll continue to look in all possible directions until the end of this year. Then again, when the LHC will start again at 13 TV in 2 years from now. Over the past 10 years, we have made huge progress in painting the portrait of this very special particle.
The exploration of the Higgs sector, the Higgs boson and the Higgs field, is a window into the unknown. So the Higgs is incredibly important.
So the LHC did not appear overnight. It was the result of decades of scientific ambition. Gauthier, what were the scientific and historical motivations that led to the decision to build it?
Okay, so as you said, it is only the culmination of a long history of colliders, which started in the 1980s. In fact, we saw Carlo Rubbia in this film. So it started with the SPP-S, where the W and Z bosons were discovered in the 80s. And at the same time, people were already thinking at the LHC as a new machine. But in between, in the same tunnel as the LHC, there was an E+, E- collider called the LEP. And from the result of the LEP, it's most of what we know about electronic physics was measured there. I mean, it was a really important collider. And then in the US came another collider, a proton-proton collider, proton-antiproton, in fact, collider, called the Tevatron at the Fermilab laboratory next to Chicago. And then after the end of the LEP, 10 years after, we had the LHC, which is the most powerful collider ever built, not only in energy, but also in intensity. And it's because we have so much data at the LHC that we can do the nice science that we do now. So.
Thank you. That's indeed wonderful, and we'll get a chance to develop all the threads you've brought up. But Oliver, the LHC is one of the most technologically complex machines ever constructed. What were the key engineering challenges in designing and building it?
Yeah, I think the key engineering challenge was certainly the magnet system for the LHC. As you've seen in the video, conceptual designs for the LHC started already in the mid-80s. And the mid-80s was also the time when the first accelerator or collider that used superconducting magnets for bending the protons in a circular trajectory was started operation. That was the Tevatron. So that was the first sincere use of superconducting magnets. And since then, the LHC has really pushed the technology over the last 25 years, or since the start of the Tevatron. It really shows the culmination of that technology to pushing really the limits there. It's the highest magnetic field ever done. It's a twin aperture magnet design that allows you proton-proton collision, and it requires the magnets to be cooled down to very, very cool temperatures of 1.9 Kelvin, implying the largest cryogenic system ever built for the LHC. So this is, for me, clearly the biggest challenge. On top of that, the LHC is a very complex machine with thousands of different circuits which have to be perfectly synchronized. Therefore, the control system and the control of all the circuits in unicism is really an enormous challenge, and only possible with modern controls technology.
That indeed sort of conveys the scale and complexity of the endeavor and of the machine. And of course, on the one hand, you have the accelerator, and on the other, you have the detectors, Atlas, CMS, ALICE, and LHCb, which were designed not in a vacuum, but alongside the accelerator itself. So, Gauthier, what makes these detectors so exceptional, so unique?
Yes, so there are 4 large experiments at the LHC, which were indeed designed to cover all the physics spectrum that you can get from this collider. So there are 2 large experiments with a wide spectrum of physics that we call general purpose experiment, which are the Atlas and CMS experiment. So those 2 experiments are very different in the way they have been designed, but they cover the same physics. And because they are different, they are really complementary. So they can cross-check each other, which is really important. In particular, when you make a discovery as important as the Higgs boson, you'd better make sure that the other experiment sees the same observation. Now, there are 2 other experiments which are more specialized. One is LHCb, and LHCb is conceived a little bit like a fixed target, even though it's looking at collision data. And thanks to this particular geometry, they can look at those particles which are made of heavy quarks. That's what we call flavor physics. And using these heavy quarks, they can look at the difference between matter and antimatter, which is really looking at something that one of the most important puzzle in modern physics, which is the cosmic imbalance between matter and antimatter. And then there is a 4th experiment called the ALICE experiment, and they are mostly specialized in looking at a special form of nuclear matter, which is called the quark and gluon plasma, and which prevails in the very early universe, a few microseconds after the Big Bang, and that all the experiments are looking at, but ALICE is really specialized in this kind of physics. And so all the experiments have been designed with this purpose in mind for doing the best physics, and they have been performing extremely well during the last 15 years.
Thank you, Gauthier, and thank you, Oliver. We'll of course get a chance to speak to all 4 experiments tonight, but before moving on, let's go over once again to Emma.
Thank you, Davide. I'm back here with Jörg, and it's been very exciting on the LHC Island. Can you just show our viewers what's just happened?
Exactly. If you look on the screen up there in the middle, which says Iron Physics Adjust, you see exactly now the beam has been prepared, ready. We've declared the mode stable beam, which means that for the experiment, everything is fine and they can ramp up their detectors and start taking data, just as we did it, as we have this live.
Amazing. And what do you remember in the days leading up to the very first beam of the LHC in September 2008?
Well, the September 2000 event was a very special event because we tried to start up a machine with thousands of visitors around the site, the press, everybody, ex-director generals, etc. So we had to be sure that everything would work. So in fact, a month before, we tried to test everything, rehearse, test the instrumentation, etc., to be absolutely sure that on the D-Day, everything would work, at least that's what we could control. Of course, you can never be 100% sure that everything's perfect, but at least you want to minimize. And in fact, on the very day, in fact, when we started here in the morning, everybody was very nervous because beams in the machine for the first time. But in the end, fortunately, with all the good preparation, but also I think all the engineering teams of CERN have contributed to this. In fact, the beams went around in 1 hour. In fact, as things went on and things were smooth, in fact, everybody relaxed and it became a fantastic day.
Thank you very much, Jörg. Back to Davide.
Thanks, Emma. And speaking of beams, why don't we watch a short film about beam intensity to better understand what's actually going on?
Inside the 27-kilometre ring of the LHC, beams of protons circulate at nearly the speed of light, divided into thousands of bunches that collide at 4 major experiments. The performance of particle colliders is usually quantified by the beam energy and the luminosity. In the LHC detectors used for particle physics analysis, an important factor is the number of collisions. The greater the amount of data, the greater the probability of discoveries. The instantaneous luminosity indicates how many protons pass per second and per surface area at the point where the beams intersect. Instantaneous luminosity is a measure of the intensity of possible particle collisions at the LHC and is crucial for researchers to find new particles such as the Higgs boson. The more protons there are in the beam, the greater the instantaneous luminosity will be. To clarify, for Atlas and CMS, every 25 nanoseconds, there are approximately 60 to 70 collisions, or 2.4 billion collisions per second, for these two experiments. For the next chapter, High-Luminosity LHC, or HLLHC, the goal is to have 200 every 25 nanoseconds, or 8 billion per second. To prepare for HLLHC, CERN has modernized the entire chain of injector accelerators. This upgrade, known as the LHC Injector Upgrade Project, or LIU, was completed in 2021, and the gradual commissioning of the beams took place between 2021 and 2025. The goal is simple but ambitious: to create beams that are both more intense and more precise. The LHC design considered a bunch with an intensity of 1.15 times 10 to the power of 11. In today's LHC, each bunch carries around 1.65 times 10 to the power of 11 protons, thanks to the partial use of LIU beams. With the upgraded injectors, each bunch can now hold more than 200 billion, while keeping the beam size under control. From LINAC 4, the protons are boosted through the booster, the proton synchrotron, and finally the super proton synchrotron before entering the LHC. In 2021, the LIU beam was commissioned, and in 2025, the SPS delivered the target beam for the first time. Bunches of 2.3 times 10 to the power of 11 protons with the required emittance or beam size. Thanks to this, in today's LHC, each bunch carries around 1.65 times 10 to the power 11 protons, thanks to the partial use of LIU beams. The next milestone will come in 2026 with the reliability run, where the injector chain will operate daily with LIU beams for months at a time, demonstrated that the upgraded system can fill the collider reliably for the high luminosity era. With the LIU beams, the new high-field quadrupole magnets to focus the beams, and innovative crab cavities, this injector upgrade will allow the high-luminosity LHC to increase its performance by a factor of 10 beyond the original design. The result? Billions more collisions and an unprecedented harvest of data to push the boundaries of our understanding of the universe.
That's indeed plenty of collisions. But now let's step back once more to the LHC and focus on what the LHC has done with all that scientific and technological effort we've been talking about, namely its performance and discoveries. Over the years, the machine kept getting better, climbing up in energy, in luminosity, and in the sheer number of collisions it could deliver. Bettina, after an initial setback, the LHC ramped up quickly. How did it evolve in energy and luminosity from its first collisions to today?
Well, starting from its first collisions in 2009, the physics running of the LHC began in 2010 at a center of mass energy of 7 tera electron volt, 7 TeV. That was at the time the highest ever achieved collision energy in the laboratory. And then in 2011 and 12, the performance of the LHC steadily increased. And the LHC also at the time exceeded the original luminosity targets already, and was running at then 8 tera electron volt. And all of this culminated in the discovery of the Higgs boson in 2012. Then, after a first long shutdown, the energy of the LHC was again increased to 13 TeV, and steady performance improvements happened over the years. And after a second long shutdown, now we are running at a record energy of 13.6 TeV. But actually, this is not the most striking thing about the LHC. I would say it's much more. It was absolutely essential to increase the luminosity, and that was really the main achievement of the last years. And as we have heard also in the film, that happened during the long shutdown 2, where the LIU, the LHC injector upgrade, allowed for a very important increase in brightness of the beams injected into the LHC. So beams that were much more intense and more densely packed. And this allowed then many more collisions happening for the experiments. And actually now every single LHC fill allows to produce 3 times more data than in the original LHC design.
That's remarkable. And thank you for mentioning the Higgs boson, by the way, because that of the Higgs boson is perhaps the most well-known scientific discovery at the LHC. We're talking about 2012. Gauthier, can you please walk us through the event and why it was such an important breakthrough?
So it was an important breakthrough because the Higgs boson is really the cornerstone of our theory of particle physics that we call the standard model of particle physics. And it is really important because the discovery of the Higgs boson is the proof of the physical existence of what we call the Higgs field. And the Higgs field is responsible for the mass of the particle. Not only the W and Z boson that I was talking before, but all the particle of matter, the quarks and the leptons. So it's quite remarkable because this transition between non-massive particle to massive particle occurred at a very early stage of the universe, a few picoseconds after the Big Bang. So we are really looking at the very birth of the world as we know it. And without the mass, there would not be any matter as we know. No matter, no atoms, no molecules, no life, no nothing. So this is really important. It is really related to our very existence. So that's why it's very exciting. Now, the discovery itself is something that was also very much expected by the physicists because they were looking for this particle for decades. Myself, I was looking at the Higgs boson when I was working at LEP in the beginning of the 1990s. So it was a very long journey where theoretical prediction and experimental searches were crossing each other. And in the end, the LHC was the only machine where this discovery was possible after the discovery of the top quark at the tevatron. So it was extremely exciting. It was an achievement. I think it's one of the most wonderful discovery in the history of particle physics, certainly, but also of all of science. And I'm quite proud, and I think everybody should be proud at CERN to have been part of this wonderful discovery.
It is indeed. It is indeed. And of course, this allows us to stress that the accelerator is an important half of the story. All those collisions cannot be exploited without the giant detectors built to catch the products and the thousands and thousands of physicists behind them. So let's now go to the 4 experiments live in their own islands. Atlas, can you hear me?
Oh, yes, we can.
Wonderful. I can hear you well. So we were just talking about the Higgs boson. In 2012, Atlas and CMS announced the discovery of this remarkable particle. Could you please explain a bit more in detail what the Higgs is and why its discovery was so important?
Hi, I'm Sarah. The Higgs boson, as mentioned, is the cornerstone of our best model of particle physics in nature, the standard model, where it allows us to explain better how particles get mass, why some are lighter, some are heavier. And it was predicted in the 1960s, but it's only with the LHC in 2012 that we managed to measure enough of its footprints to confirm that, with some proof, it really does exist as a particle. And then we continue from there to measure more of its properties and in higher levels of detail so that we learn more about the fundamental interactions in nature.
But of course, the program at the LHC reaches well beyond the Higgs. Could you please give us a sense of the range of physics Atlas has explored?
This is very true. Beyond the Higgs boson, we also measure various other properties of standard model particles, for example, the bosons related to the fundamental fields, or also the heaviest fundamental particle, the top quark, where we are now moving into precision measurements of also spin effects and things related to quantum effects. But I said the standard model is our best model. It's so good that it also tells us that there are things we can't explain, like, for example, the origin of dark matter. And this is where another side of the effort comes in, where we have searches for new physics. And they can also happen in precision measurements with small deviations. But we have also many, many direct searches for new particles, such as things stemming from supersymmetry or additional light or heavy bosons, additional Higgs bosons, even more exotic theories. And the signs of these can show up in the detector as many different patterns of visible or even invisible things, which we then record. And all of these searches and measurements require slightly different approaches. And it's one of the beauties of this multifaceted experiment and collaboration of people that we can manage to do that work and smoothly do all of these things and analyses in parallel.
The detector, indeed, is a big machine and a very complicated one, and you've been running it for a very long time. So what have been the main challenges in doing so, and any specific anecdote you could recall?
Yes, indeed. I mean, the LHC detectors are some of the largest scientific instruments that we've ever built. The Atlas detector itself is about 8 stories tall in a cavern deep underneath us where we're standing right now. And these detectors are 20 years old, and they're really custom built and designed detectors and electronics to do the physics that we want to do. As the LHC has continued to improve its performance, we're well past the kind of delivery of luminosity and data that we had originally designed the detectors for. So keeping up with the success of the LHC on the detector side has also been a tremendous challenge. And we have a large group of very dedicated people who continue to improve the detectors, improve the performance, and try to essentially keep up with the LHC as they deliver us more and more data.
Thank you very much, Atlas. That's wonderful. I would suggest we now move to our friends at CMS. Can you hear me?
Yes, we can hear.
Wonderful. So, focusing on the years that followed the discovery of the Higgs boson, what have we learned about it, and what do we still need to understand?
So in the past decades, we had made really unforeseen progress in understanding of this fundamental particle, which is considered one of the most important particles we have in our model. So we continued measuring more and more precisely its properties, for example, the mass, the spin, how it couples to other particles. We are making a leap forward in our understanding of how it interacts with itself. And those are extremely important measurements to be made because they are helping us in understanding addressing three important open questions, fascinating questions that we have that were briefly touched upon before. How the universe essentially got its shape soon after the Big Bang, what is the visible mass budget in the universe itself, and especially how it will evolve over time. So really birth, current status, and evolution of the universe. And by measuring these properties as precisely as possible, we are really pushing our knowledge. We are testing the so-called standard model, but we are doing actually much more than that. We are trying to look for small, tiny deviations that could emerge from a fundamental physics that we have not really seen directly, and we are looking for because it may explain many of the open questions that we still have as of today. So the discovery of the Higgs boson in a way close the chapter of the standard model, but open the window towards the unknown.
You mentioned a very important word, which is precision. Because of course, without precision, you cannot do science. So how do we reach precision in these particle physics measurements?
There are many elements to it. The first one is actually related to the accelerator. So the LHC has provided much more data that we had anticipated. So we had a large collection of proton-proton collision, especially for the Higgs, at our disposal. So we are looking at that as precise as we can. We have really continued improving our detector to make it more and more capable. We are deploying, for example, artificial intelligence to select events or collision images as precise as we can and studying them as precise as we can. And one important element, time. So in order to make precision measurements, we need decades of time of thousands of physicists that really look into all the possible effects and the detector impacts, for example, on a given measurement. And this is, I think, a good time to pass it on to my colleague, Giulia Negro, because one key element of precision is quality of the images that we are taking. So how we operate the detector is absolutely critical.
Yes, indeed. Thanks, Anadi. Yeah, thanks to the efforts of thousands of physicists, engineers, and technicians, we really managed to operate this incredible detector in the most efficient way. And we have a lot of shifters every day monitoring continuously the detector, so you can see them behind me. And they are here every day and night. And then we also have a lot of experts, detector experts, that they are ready to jump in immediately in case there are issues while we take data. Then after all, we collect all the data, we really check them carefully so that we can assure high data quality for all our physics analysis. And yeah, thanks to all the continuous calibration, alignment, and monitoring, we manage to really characterize the detector response with extremely high accuracy.
Well, I imagine keeping such a large detector performing so well must have been challenging. So do you want to tell us something more about it?
Yeah, indeed, it has been an enormous challenge, in particular in the last years. So CMS is, again, a very complex experiment. It has 200 million of channels operating in a very harsh environments of radiation. And it really required a lot of constant monitoring and efforts from a lot of people to maintain its performance over more than a decade. In particular, there are a lot of challenges because thanks to the excellent performance from LHC, we surpass a lot of the design specification from several systems. So we really needed to increase the attention related to a lot of different components that were aging, they were affected by more and more increasing levels of radiation. So a lot of efforts from a lot of different teams ensuring that the components were replaced when needed and everything was kept under control. And yes, I really think that the results of CMS, the long-term successful term of CMS is really thanks to all the people behind it.
Thank you. Thank you very much. I guess it's now time to move to Alice. Alice, can you hear me?
Yeah, welcome to Alice.
Thank you. Thank you very much. So we've heard that Alice was designed and built to study this quark-gluon plasma. Can you tell us something about what the quark-gluon plasma is and what we've learned about it along the way?
Yeah, one of the greatest achievements of Alice has been creating tiny droplets of the matter that filled the universe a few microseconds after the Big Bang. And by colliding atomic nuclei made of lead, the Large Hadron Collider recreates these extreme conditions. And we have in Alice measured temperatures above 3 trillion degrees Celsius. That is more than 100,000 times hotter than the center of the sun. And we have observed that this matter is remarkably dense and opaque. So even heavy quarks, which are made in the collisions, they don't exist in our everyday world. They struggle to get through it. They interact with the quark-gluon plasma, they lose energy and get dragged away by the plasma flow. And this demonstrates how strongly interacting the quark-gluon plasma is and helps us understanding the matter that filled the early universe.
And speaking of things that changed and evolved over time, Alice too has changed, right? And a great deal between run 1 and today. What can the experiment do now that it could not at the start?
Indeed, it has been transformative. We underwent an upgrade 5 years ago. Alice now records 1,000 times more data than before. This means measurements that took a decade once is now can be done now within a few days. So this gives us entirely new view of rare particles such as heavy quarks. So we can use these heavy quarks as tiny probes that interact with the quark room plasma and lose energy, for example, or create collective flow by the plasma flow. So the result is a much sharper picture of the hottest and densest matter ever created in the laboratory.
That's quite interesting indeed. And we've heard that detectors are complex, right, from your colleagues. And I imagine that running ALICE for so long and so well must have been extremely difficult and challenging as well. So could you tell us something about that?
Ciao Davide, thank you for your question. I'm Silvia Pisano, ALICE Run Coordinator, and I'm responsible of the experiments data taking. One of the main challenges of running such a large experiment is keeping everything in sync with the LHC and the other experiments. It's very much like being part of an orchestra. Everyone has to come in at the right moment, stay precise, and adapt continuously as the music evolves. And the results of this ongoing concert that was ongoing up to a few minutes ago is the collection of millions of particle collisions, which we use to study the fascinating phenomena that Kai mentioned earlier. And in practical terms, this means recording more than 300 gigabytes of data to disk per second. So it's a rich and complex data set. Beyond the technical aspects, there is another very important aspect that makes the data taking experience rich from many points of view. And it is the fact that we have to continuously train new shifters from all around the world so that they can work together to run the experiments and collect the data, sometimes facing unexpected situations. This is a demanding but a very rewarding task. And seeing our colleagues from many different countries work together so effectively and deal with the complex situations so well is one of the most valuable results of a large experiment as ALICE.
Thank you. Thank you very much. Now, I would ask our friends at LHCb if they can hear us.
Good afternoon, Davide. Hello.
Good afternoon, Paula. So, one of the deepest puzzles in physics is the apparent, at least, asymmetry between matter and antimatter. How has LHCb helped us study and perhaps understand it?
So thank you for the question, Davide. So my name is Paula, and I'm on the Run Coordination team of LHCb together with Federica and Flavio. And indeed, Run 3 is drawing to a close. We can hardly believe it. It's a very emotional moment for all of us here. It's a chance to reflect on our achievements. So LHCb is truly a unique experiment at CERN. So we have been designed not to focus on the search for new particles, but rather to measure tiny differences in the behavior of matter and antimatter. And these differences, as you intimated, Davide, with your question, they really strike at one of the fundamental mysteries of modern physics, because the universe that we see around us is made predominantly of matter, whereas we know that at the time of the Big Bang, matter and antimatter were created in equal amounts. So the success of LHCb in attacking this mystery has exceeded our wildest expectations. LHCb has transformed our understanding of matter-antimatter asymmetries. We've measured the fundamental parameters with an order of magnitude improvement in precision. We have uncovered asymmetries in completely new systems. But what was completely unexpected, I think, was that LHCb would also become a discovery machine. We have discovered 75 new particles, and this includes exotic forms of matter, such as pentaquarks. And just last week, we announced the discovery of the doubly charmed omega baryon. This is a particle whose existence had been anticipated for decades. So it's just the beginning. We have a treasure trove of Run 3 dataset. We have our upgrade to look forward to. And with this huge amount of data, we will improve, again, an order of magnitude in precision. We're very excited for the future. And all of this happens because of this fantastic community of engineers, physicists, technicians, and working together to unravel the mysteries of the universe. It's been the greatest joy.
Congratulations for the many hadrons, Paula. That's amazing. And you mentioned your Run 3, so LHCb having an excellent performance. So what do you think were the key enabling factors for your successful operation?
So LHCb went through a major upgrade during the long shutdown too, right before the beginning of Run 3. So our tracking system was upgraded to include Velo, UT, and Sci-Fi, and also our charged particle identification detectors, Reach 1 and Reach 2, were upgraded. So detector innovation is fundamental to cope with these challenges in physics and to reach our goals. And also detector innovation has lots of impact, not only in particle physics, but also in medicine. But it's not the full story, because the great success of the LHCb data taking is made possible thanks to all the shifters that you can see here, and also our experts on call who are always ready to jump in anytime in seconds, maximum minutes, and to not waste our precious proton-proton collisions.
Thank you. Thank you very much. Actually, thank you all. It has been wonderful to have you here with us tonight. Let me come back to the table for a couple more questions before moving to the future. Now, Bettina, from the machine side, what did it take to deliver the collisions that made the discovery of the Higgs possible?
Well, there were actually two main challenges. So firstly, was the increase in energy that we mentioned already. And this was actually needed to surpass a threshold to produce the Higgs boson. The second main ingredient was the increase in luminosity, because we actually needed not to produce one Higgs boson, but we needed to produce thousands of Higgs bosons, and we needed to get enough data to actually distinguish and study the Higgs boson, which is buried in the middle of millions, billions of ordinary events. So that's the main things. And for the energy increase, as Oliver already mentioned before, the main ingredient was the design and production of the superconducting magnets, of this incredibly complex cryogenic system that is needed to cool them down. But also many other ingredients like fail-safe machine protection system, a very complex collimation system, precise beam instruments, whatever. So many systems had to play together. And for the luminosity increase, there we needed to produce throughout the full CERN accelerator chain very stable and bright beams to have really a lot of collisions for the LHC. And also we needed to run really reliably all these machines to provide all the data for the experiments.
Well, and speaking of events, of luminosity, of Higgs signals hiding among them, one thing is clear. The Large Hadron Collider produces an enormous volume of data, which demand a vast computing infrastructure. Gauthier, how do physicists store, distribute, and analyze all this?
Yeah, thank you for this question, because we should not forget the importance of computing for what we do. As you said, we are talking about the 4 experiments that we have seen are producing a lot of data, and it's a huge amount because there are lots of data that's produced by the collider itself. So we have heard this number of more than 2 billion proton-proton collisions per second in the heart of the experiments. And the experiments themselves are taking a three-dimensional frame of these collisions 40 million times a second. So you can imagine each of these frames is 200 million pixels, three-dimensional pixels. So it's a huge amount of data, and actually we cannot store all of this data. So that's why we have systems in the experiment to select the interesting data, including farms of computers which are on site in the next to the experiments, which are selecting the data, and then we can transfer this data to the main data center at CERN, which is called the Tier 0, and we are talking of rates of several tens of gigabytes per second, so it's huge. And then this data center Tier 0 is itself not only storing the data, the raw data on disks and then on tape, but it's also distributing all this data in many data centers in the world. So the big one we call Tier 1s, and there are several in Europe, but also in the US and in other parts of the world, and smaller data centers that we call Tier 2s. And all these data centers are linked in a network that we call the Worldwide LHC Computing Grid, WLCG, and this network is what allows all the physicists contributing to the experiments all over the world to access the data and to analyze the data for doing the science that we do. So all this infrastructure, computing infrastructure, has been put in place over the last 20 years and is working remarkably, and that's what allows us to actually access the data and make the physics.
There's a word we kept hearing tonight over and over, which is luminosity. So before we move to our next topic, namely the future, let's watch a short film explaining what luminosity actually is.
Over 1 billion collisions per second, 3,600 seconds per hour, more than 2,000 hours per year. Since it started taking physics data in 2010, the Large Hadron Collider collided protons about 50 million billion times. That's about the number of grains of sand on an average 10-kilometer beach. And yet, if we ask, what will happen in the collision that's about to take place, the answer is simple. We don't know. This isn't because of the limitations of our instruments or calculations, but because particle interactions are governed by quantum mechanics. This means that they are fundamentally random. No single collision can tell the full story, but observing a sufficiently large number of collisions allows us to uncover patterns in particle behavior. Our current description of how nature works on the smallest scales, the standard model of particle physics, has been tested to incredible precision. But it doesn't explain everything we observe. For example, it doesn't explain dark matter, a mysterious form of matter that we cannot see, but whose effects we observe throughout the universe. It also doesn't tell us why there's more matter than antimatter in the universe, rather than the amount of both being equal. However, since the standard model has been tested so precisely, anything beyond it is likely to appear as either a very small deviation from expectations or as something extremely rare. To get a sense of how rare, let's look at something that we have already found: the Higgs boson. We cannot detect the Higgs boson directly, so instead, we detect the particles that it decays into. For example, when a Higgs boson decays into 2 photons, the photons fly out in different directions through layers of detector systems designed to record them. Only about half of these pairs can be confidently identified, and only about 1 in 500 Higgs bosons decays this way. To produce a Higgs boson in the first place, we need to collide protons about 4 billion times. Many decays are needed to reveal a pattern in the data. This plot was one of the key plots shown during the Higgs discovery announcement in 2012. The signal here corresponds to about 200 Higgs bosons decaying into photon pairs. Imagine how many collisions were needed for this. Instead of discussing these experiments in terms of their billions of collisions, particle physicists use a quantity called luminosity. The number of collisions we accumulate over a period of time is described by integrated luminosity, and the speed at which an accelerator delivers those collisions is the instantaneous luminosity. Over the past decade, the LHC has been steadily increasing the speed at which it delivers collisions. But the questions we are now trying to answer demand even more data and higher levels of precision to give us access to even rarer processes. Simply continuing at the current rate would not be sufficient. We need a dramatic increase in luminosity. To provide this, CERN is now working on a large-scale upgrade to the LHC, the High-Luminosity LHC. We're also transforming our particle detectors to help us better record, reconstruct, and identify the rare processes that we care about. Ultimately, how far we expand our understanding of the universe depends on how many more collisions we produce and how much more information we extract from them. Improving both will unlock the next phase of exploration at the LHC.
In science, every ending is also a beginning. During its third long shutdown, the LHC will undergo major upgrades to become the High-Luminosity LHC, which is set to deliver much more data. So let me turn for one final time to our guests to look ahead to what's still to come. Gauthier, this moment marks the end of a physics run after years of operation. Emotionally and scientifically, what does this last beam represent for the teams?
Yes, you said it's very emotional because it was a wonderful journey, this first part of the LHC, I must say. In particular, the very end, what we call the run 3, has been extraordinary because we have recorded much more data in a few years, in 3 years, than that we had before. And this is very emotional because we have seen also evolving the quality of the way we analyze the data and all the things that people have invented to get the best of this data. So not only the luminosity has increased, but also the quality of the detector, as we've heard from the previous speakers, and also the quality using machine learning, deep learning, artificial intelligence techniques. We have really improved a lot the way we look at the data and the quality of our results. So emotionally, it's a little bit sad to see that in a few days from now, it will be the last beams in the LHC for a long period. But we are sure that we will come back and we will be even better and we will take even more pleasure in analyzing the data. Thank you. So we are looking forward really to the new data with the High-Luminosity LHC.
It is emotional, and that's why we're here to celebrate the LHC. In the coming days, we've said, the machine will enter long shutdown free, as we said, LS free. Bettina, why is such a long shutdown important? Why do we need it?
Well, a very good question, Davide. Well, one has to understand that we are operating the CERN accelerator complex 24/7, usually during several years, where we only stop for short periods during winter breaks to perform maintenance of the machine, some consolidation, and some small changes to its equipment. But long shutdowns, they are really there to perform significant upgrades. So long shutdown 2, for example, was dedicated to upgrade the LHC injector chain to increase the luminosity. But now long shutdown 3 will be dedicated to prepare the LHC for its next chapter, really for the high luminosity LHC era. And actually to upgrade the LHC, it is not as simple because first, for example, one has to warm up the machine to perform really important changes to the machine, one has to warm it up from 1.9 Kelvin to room temperature, and already this takes of the order of months. And then there will be really extremely significant upgrades. One has to also dig new tunnels, access shafts, pull kilometers of cables, and upgrade, in particular, the superconducting magnets again. Many equipment, RF cavities, beam instrumentation, vacuum systems. I only mention a few of them. It's a huge endeavor and logistics that is needed. But actually, the gain that we get from these 3 years or these few years of long shutdown upgrade activities in terms of machine performance, reliability, and increasing the number of collisions to study in much more precision the Higgs particle and so on. This is really much more exceeding the loss that we have by not taking data during these 3 years.
We've said that the whole accelerator complex will undergo major upgrades. Oliver, would you mind listing some for us?
So at the cornerstone is certainly the High-Luminosity LHC upgrade, where we take out of the machine about 1.5 kilometers of existing elements and replace them with more technology advanced new equipment that we have developed over the last years. So it's about 1.5 kilometers in total, concentrating the work next to the main experiments, Atlas and CMS. In addition to replacing the elements in the tunnel, we also built new underground structures of the same length about, new galleries and caverns that we're now starting to fill with new components, power converters, protection systems, electronic racks, and so on. The crown jewel for the HiLumi upgrade is certainly the new focusing quadrupole magnets, which on its own a marvel and really a technology challenge. But I think LS3, one should not focus only on HiLumi. There are many other areas too. Certainly one of the big priorities and challenges will be to bring the machine back to operation within 4 years. But on top of that, we have an isotope program, Isolde, which also undergoes a major upgrade to increase the performance for that system. And for the SPS, our pre-accelerator for the LHC, we have a dedicated fixed target program, which we label as a North Area. And that complex also undergoes a major upgrade to assure that we can perform and provide fixed target physics for the coming decades. So these are all major upgrades going on.
Focusing once again on the HL LHC or High Luminosity LHC, the machine will produce far larger datasets than ever before. Gauthier, is there a chance you could tell us something about the physics this will open up, especially for rare processes?
Yes, so first I would like to mention that the machine is going to be upgraded, but also the large experiment, Atlas and CMS, are going to be upgraded, and the upgrades are really exciting because they are very bold, and we will be able to reach a much better physics and be a much better sensitivity on, in particular, the very rare processes. So I was talking about 200 million pixels before. Now we will be talking about billions of pixels, including a new dimension, which is timing. We will also have timing, so we will be able to really make the best of the much more intense collisions that we will have at High Luminosity LHC. And with this amount of data, which will be about 6 to 10 times more data than what we got in the LHC, we will be able to look at some of the extremely rare processes involving the Higgs boson. So some of them were mentioned. There are very rare decays of the Higgs boson, which are important because we can look at the couplings of the Higgs boson to the second family of quarks and leptons, with the muon, for instance. Okay, try to go even further than that. And we can also look at the interaction of the Higgs boson with itself, because the Higgs boson has a mass, and since the Higgs boson is responsible for the mass, it interacts with itself. And it turns out that this process is extremely important to understand how the Higgs field works and to understand why our universe is stable That's simple. So this is a very fundamental question. And this we need all the data of the high-luminosity LHC to really be able to measure this parameter that drives the stability of the universe. So it's quite exciting. Of course, there are many, many other things. The experiment up to now have published more than 5,000 scientific publications to peer-reviewed journals. And each of the experiment is publishing between 50 and 100 publications per year. So it's a huge crop of physics, and this will continue even better with the better quality of the data at high luminosity LHC, thanks to the upgraded detectors.
Well, the stability of the universe is indeed a relevant question. And of course, the high luminosity LHC, speaking of long term, because the stability of the universe surely connects to long term, is part of a long term vision. So what could be the next big step for CERN and for accelerator science worldwide after HiLumi?
So as we said, the LHC is colliding protons. And so there is a fundamental uncertainty that comes from the fact that protons are not fundamental particles, but are composite particles. They are made of quarks and gluons. So if you really want to do a leap forward in the precision with which you measure the interactions of the Higgs boson, you need to go to a different kind of collisions, and these are E plus E minus collisions. So if you remember, the LEP collider was also colliding electrons and positrons, but what we want to do is a collider that would be between 100,000 times and 1,000,000 times more intense than the LEP collider, and this is called the FCCEE. But if you want to do that, you need to have a much larger ring, and we are talking of a ring that would be 91 kilometers in circumference, 3 times larger than the tunnel of the LHC. So this is the big project that not only CERN but the European community, through the European strategy upgrade that was just adopted by the CERN Council a couple of weeks ago. This is really the big project that CERN is willing to do. This is extremely ambitious, of course, and there are still lots of work to be done. We are talking about a collider that will start in 2045. But this is extremely exciting, and that's the way where we could really reach a precision on understanding the Higgs boson, but not only the Higgs boson, the 4 important particles, WZ and the top quark and the Higgs boson, and that will really help to understand and try to find a indication of what is the new physics beyond the standard model.
Thank you. Thank you very much. Of course, building the high luminosity LHC is also a huge, massive industrial effort. So, Oliver, how are industry and international partners involved in this process?
This is a core goal for the high luminosity LHC upgrade, is that we involve partner laboratories and industry from the beginning. To increase the performance of the LHC by factor 10, roughly, really requires or implies technical breakthroughs in many, many, many areas. And what should maybe highlight here is that we started dreaming about the high luminosity LHC already 99, 2000, before the LHC even started operating. And we started thinking about what technologies do we need in order to push the envelope even further for the performance of the accelerator. And in 2000, we started really close collaboration with many laboratories worldwide, not only in the US, but in Europe, all over the place. And then after the first ideas developed, we started working very closely with industry from the beginning. It's also in the mandate of CERN that we don't do our research in isolations, but it's one our mandate that we develop technologies which we then bring out to industry and other laboratories. So these efforts cannot and must not be done in isolation at CERN. It's really at the core of our mandate that we do this in very close collaborations. Many of the components now that will be installed in the high luminosity LHC come from industry, which have been partners with us from the beginning.
Well, what a story this has been. From the first ideas behind the LHC, to the first beams, to the discoveries that pushed our understanding of the universe forward, we've been looking back at an extraordinary scientific adventure. And what comes through, above all, is that the LHC is a human story, built on curiosity, on the thousands of people choosing to work together on this amazing and massive scientific project. A huge thank you to our guests here in the studio. And a big thank you as well to all the teams who joined in live from the experiments, Atlas, CMS, Alice, and LHCb. Last but not least, thanks to all the people who are right now behind the cameras and the screens. The LHC has already carried us a long distance, but the journey is far from over. Over the coming years, it will be reborn as the High-Luminosity LHC. And the next great chapter of exploration is already on its way. So thank you all, and thank you for watching. And we hope to see you again very soon here at CERN.
What if we could open a new chapter in our understanding of the universe? CERN houses the largest particle accelerator in the world. Among its many discoveries, in 2012, the Higgs boson was found. The discovery shed light on the mystery of how particles gain their mass. Studying the Higgs boson's unique properties may be the key to understanding some of the deepest mysteries in physics. But the Higgs is a very elusive particle, appearing in only about 1 in a billion collisions at the LHC. Enter the High-Luminosity LHC. By vastly increasing the number of collisions, this new machine will allow the study of the Higgs and other rare phenomena in greater detail, opening a new era of precision in physics research. In particle accelerators, luminosity measures the amount of collisions. The High-Luminosity LHC will have a higher collision rate, resulting in more data and therefore a higher precision. To achieve a higher collision rate, many new technologies had to be developed and built in collaboration with experts from all around the world. So-called crab cavities will tilt the proton bunches of the beam at the collision points, and stronger magnets will squeeze the proton beam more than ever before to increase its density. To make it all possible, there will be superconducting links that provide the high electrical currents needed. In total, the High-Luminosity LHC will reach 400 simultaneous collisions every 25 nanoseconds. Collecting more data per day will let us map out the vast space filled with open questions about the Higgs field, the way it works, and many other questions during the coming years. This isn't just about physics. It's about developing new technologies, bringing nations together, and training the scientists of tomorrow. Many of the technologies developed at CERN end up transforming our everyday lives. The High-Luminosity Large Hadron Collider, a new machine for a new era of discovery.